So one of the fun things that I did in last year was obtain my data science professional certificate from IBM. And that course culminated in a capstone data science project, kind of covering all aspects that I learned in the courses. This is it. This is Winning the Space Race with Data Science by me, Joel Knapp. This is my outline of the presentation I'm going to walk you through today, beginning with an introduction, my executive summary, methodology, the results that I drew, and the conclusions that I came to. Um, all of my work is stored on GitHub. So there's not that much code in this presentation, but if you'd like to see the Python code or the SQL code that I used to do all of this data science work, that's on my GitHub. I'm happy to link it to you. This project, I take the role of a data scientist working for a company, Space Y, and we're looking to compete against SpaceX in terms of their Falcon 9 rocket launches. So what I'm trying to do here is predict if the first stage of the rocket will land successfully. Why am I doing that? Because SpaceX launches cost a lot less than their competitors. And one of the reasons that they cost so much less is because they often reuse the first stage of the Falcon 9 rocket launch booster. Therefore, if we can determine if the first stage will land and what variables make it a better chance of landing, we might be able to estimate the launch cost, and we can use this to bid against SpaceX with our own rocket launches in the future, potentially. This is a summary of the methodology that I used here. I started with the data collection phase, moved on to the extract, transform, load process, or the data wrangling phase. I did a lot of exploratory data analysis, both in Python and in SQL. And then I created an interactive map using the Folium library and a dashboard using the Plotly Dash library, followed by some predictive analysis using a supervised machine learning classification model. Actually, a few different models that I tested, and we settled on one that drew the best conclusions. On the right, there's more granular analysis of the things that I did here, right? I extracted data with an API. I web scraped with Beautiful Soup, which is a pretty fun HTML parser. I'm transforming and loading that data using the pandas library to create data frames, sorting and filtering with SQL, data visualization using the Plotly and Seaborn libraries. As I mentioned, built an interactive map with Folium and a dashboard in Plotly Dash. And of course, there's a lot of great supervised machine learning applications built into scikit-learn, which is a Python library. Specifically, when I was doing data collection, I used a combination of an API request on SpaceX's website, and I also web scraped a lot of data about these rocket launches from SpaceX's Wikipedia page. I combined these two data frames into one large frame to get a complete picture of these Falcon 9 rocket launches. When I'm pulling data from the SpaceX website, what I'm doing is requesting data from the application programming interface and decoding it in a JSON format, which I then convert to a pandas data frame. Within that data frame, we can isolate the Falcon 9 launches. We can also do some preliminary cleaning, in particular, removing missing values here. We use the isNull method to replace them with a calculated mean, and then export that to a CSV. Now I move to Wikipedia and I start scraping some data off here with Beautiful Soup. This was my first time using Beautiful Soup, and it's a pretty cool way to extract data from a web page because we can pull things based on the HTML elements, right? In this instance, I'm extracting all the column names from the Wikipedia website, looking for the TH element in the HTML. And then I'm parsing these tables into my pandas data frame and exporting to CSV. Finally, I combine these data frames. At this point, I'm ready for the data wrangling stage, which in most cases is a lot of the heavy lifting when I'm learning data science. So I'm cleaning this data set using the pandas and NumPy libraries within Python, although of course there's other programming languages you can use to do EDA. One thing that I really wanted to achieve here was convert some of these launch outcomes, which are categorized in all different manners, into a very simple one. The Falcon 9 booster landed successfully, or 0, the booster failed to land. This makes for some pretty easy analysis afterwards. I'm using methods such as value counts to calculate the number of launches on each launch site. There are different launch sites that SpaceX uses here for these rockets. And there's different orbit types as well. So I'm looking at the number of each orbit type at occurrence and trying to glean some insight from those. Obviously, the mission outcomes are important to me, and that's why I'm creating this landing outcome label to simplify it into a Boolean 0, the rocket failed to land successfully, 1, it successfully landed, and then exporting this all back out to a CSV. In my EDA phase, I used SQL at first to query my data set and draw some initial hypothesis or insight. And then I'm plotting a lot of charts, right, using Plotly and Seaborn within Python to gain a better understanding of the data set and to make it plain to others what I can see. In SQL, I'm using queries to do some very specific things listed here, such as select the name of launch sites, calculate the payload mass for the boosters that are launched from those sites, look towards which landings were successful and what days they occurred on. And in particular, I wanted to look at booster payloads in the median range, which was about 4,000 to 6,000 kilograms. And I also wanted to look at some booster payloads on the upper echelon. What is the heaviest rocket that SpaceX launched, and was it successful or not? And we're going to touch on that again later in the presentation. This first chart we're looking at is the success rates by flight number and launch site. And to make it simple, an orange dot is a successful launch, and a blue dot is a unsuccessful launch. And I can see right away that it appears to me that the more times these rockets were launched, the more successful SpaceX got at retrieving the booster. In particular, one of these launch sites, KSC LC39A, seems like it might be a little more successful than the other launch sites. I just see a lot of orange here, and I'm going to look into that later. Doing a little bit more exploratory data analysis here, this chart is the success rates measured by payload mass and launch site. I mentioned earlier that I was curious how payload mass would affect the success or failure of these launches. And we can see that in general, it appears that a higher payload mass is a little more successful. And that this KSC LC39A launch site has an almost a perfect success rate for a mass under 5,500 kilograms and an almost perfect success rate for mass over 8,000 kilograms. So that's kind of intriguing to me. This VAFB LC4E launch site is mostly successful, but also doesn't have many launches. This is just a simple bar chart exploring success rate by orbit type. Now, these rockets can have different orbit patterns, and it turns out that some of them are more successful than others. This ESL1 orbit type, GEO orbit type, HEO orbit type, and SSO orbit type are 100% successful, whereas some of these other orbit types are more or less successful. And this SO orbit type is a failure. Now, I don't really know a lot about these orbit types. I couldn't exactly explain to you what they mean, but I can definitely glean from this that some orbit types are more successful than others, and those are the ones that we might want to force if we were launching our own rockets. You can see here, again, a chart of the success rates by flight number and orbit type. Like, we have a hunch that the more times these rockets get launched, the more successful they seem to be. And that relationship is very clear across some of these orbit types and less clear for others. For example, when I look at this GTO orbit, I see almost no pattern between the flight number increasing and the success rate. Whereas this VLEO orbit type seems very successful and also has, been one of the more recent orbit types that SpaceX has employed. This SSO orbit type, 100% successful. Now, these other ones that we noticed in the previous bar chart, ESL1, HEO, GEO, yes, 100% successful, but also only occurred once. So not exactly the relationship that I would say is reliable. Now we're looking at the success rates by payload mass and orbit type, right? We're still wondering here, how does payload mass affect the success of these rockets? And it does appear that for payload mass over 8,000 kilograms, these are some successful launches, specifically with the ISS, PO, and VLEO orbit types. Whereas again, this GTO orbit type seems to have no relationship between payload mass and success. And this SSO orbit type, 100% successful, but also they really only launched small rockets from here, between 0 and 4,000 kilograms. This is a pretty simple takeaway. When I'm looking at the success rate of these Falcon 9 rockets returning successfully, it's just gotten better over time. You know, we did have this dip in success rates between 2017 and 2019, which could be related to many factors. Maybe they were doing a large amount of launches in that period, or testing new orbit types, or testing different payload masses, and some of those were failing and succeeding. But generally speaking, over time, the success rate of these SpaceX Falcon 9 launches has only increased. Now, I wanted to create an interactive map, and I used Folium to do this. Why did I create this map? Well, I wanted to look at the success rate of launches, and I also was curious about how close these launch sites are to other locations, and where are they located in the world and why? So when looking at these launch sites used, we can see that they're all in the United States, which makes sense. SpaceX is an American company, but also they're very close to the equator line. And it turns out there's a reason for that. The land at the equator is moving very fast. The Earth is spinning, and the equator is typically moving at a rate of about 1,670 kilometers per hour. So if you launch a rocket from the equator, it turns out that the rocket is more likely to stay in orbit because it's already moving fast at the time it's launched. And something else is when these launch sites are planned, they're often close to the ocean because if you launch a rocket near the ocean and you launch it over the ocean, it's much less likely to hurt people or surrounding buildings or towns. This is the launch site that we were looking at earlier because it was very successful. This is KSC LC39A. These green markers indicate a successfully launched rocket, and the red markers indicate a failure for the Falcon 9 booster to land successfully. And this is a very clear visualization that this launch site has quite a high success rate. Now, as I mentioned before, I was curious, how close are these launch sites to different landmarks? It turns out they're pretty close. This KSC LC39A launch site in particular is less than 20 kilometers from some pretty important geographical locations like a coastline, Titusville, a city, a railway, a highway. And this is significant because these rockets travel extremely fast. And if something went awry, they can cover distances like 15 to 20 kilometers in a matter of seconds. So if something was to go completely haywire, there is a potential for danger with these launch sites being this close to these geographic locations, which is important to note if SpaceY, the company that I work for, is choosing a launch site to launch from, and what distance are they going to launch the rockets, for example? Probably to the right, not to the left. Next, I wanted to create an analysis dashboard. And I use Plotly Dash to do this, but there's lots of different applications to build a dashboard. Just to summarize some of my findings and to make it interactive for me to play with. Now, I've screenshotted some bar charts from this, or some charts from this dashboard. This one in particular, this pie chart, is analyzing the percentage of launches from each site. And we can see here that the KSC launch site that's been so successful also attributes for 41.7% of all launches. And I do have this hypothesis that we examined earlier, that the more times these rockets are launched, the more we can learn, the more we can test, and the higher the success rate becomes. We might assume there's a correlation between KSC LC39A's very high success rate and also that it being the most used launch site by SpaceX. I'm looking into this launch site in particular, and I'm determining exactly how successful it is. It is 77% successful. And we can see that this launch site is the most successful out of any of the launch sites. Digging a little deeper into the relationship between success and failure and payload mass, I noticed something. This class, again, is a 1 for a successful launch and a 0 for a failure. And when the payload mass is very low, there's only a couple successful launches. There's a lot of these low payload masses, let's say below 2,000 kilograms, that are unsuccessful in returning the Falcon 9 booster. Whereas between this 2,000 and 3,500 kilogram payload mass, there's a large amount of successes and a large amount of failures. Now I shifted the filters a little bit, and I'm looking towards some heavier rockets. And it turns out that when the rocket is extremely heavy, as in almost 10,000 kilograms payload mass, it's about equally likely in succeeding or failing, which I would consider prone to failure. Whereas when we look at this middle section here, 4,000 to 4,500 roughly, mostly failures. 5,500 to 7,000, a lot of failures, but there's a little sweet spot right here, right around the 5,000 kilogram payload mass. They seem to be quite successful. So my launch analysis dashboard was able to confirm some of my earlier hypotheses. The KSC LC39A launch site has the most launches. It's also the most successful. And we might assume that there's a correlation here between number of rockets launched and their success. If the payload mass is too low or too high, the launches are more prone to failure. And a payload mass between, let's say, 2,000 and 5,000 kilograms appears to offer the highest chance of success. At this point, I want to do some predictive analysis, and I want to use a supervised machine learning model, a classification model in particular, to determine, how can I most accurately predict whether these future launches will land successfully or result in failure? So after I separated the data sets into a training and a test set, and I tested a few different models here. I tested a logistic regression model. I tested a supervised vector model. I tested a decision tree and a k-nearest neighbors model. It turns out that the decision tree model is the most accurate in predicting the success or failure of future SpaceX Falcon 9 rocket launches on both the test set and the training set. I want to summarize this in a confusion matrix for you. Out of 18 samples, my model predicted that 15 will land successfully, and it was correct in 12 of those predictions. Now, it also predicted that 3 rockets will not land successfully, and it was correct in all of those predictions. Therefore, my model is 100% accurate in predicting whether a rocket will not land successfully, and about 80% accurate in predicting whether a rocket will land successfully. So what conclusions can I draw from all of this? Well, A, the chance of success for Falcon 9 rockets have increased over time. One launch site in particular, KSC LC39A, is the most successful launch site with a 76.9% success rate. And these medium payloads are a good bet in terms of delivering a successful Falcon 9 rocket booster launch. The most accurate model for predicting the success of these launches, in this case, was a decision tree model, which is actually quite accurate, 83.3% at predicting whether a rocket will successfully land, and 100% accurate at predicting if the rocket will not successfully land. So this insight could be used for the SpaceY company that I work for in a few different ways. We might choose a launch site like KSC LC39A or something very close to it to launch our rockets from. We might look towards medium payloads as being one of the more successful rockets that we could launch. And when we're predicting the future success of our own launches, maybe we'll use a decision tree model. It seems quite accurate. I would also add that there seems to be some orbit types that are a little more successful than others, and if we can force an orbit type with our launches, we probably want to lean towards those ones that had a higher success rate. And thanks for listening. If you found any of this interesting, please don't hesitate to contact me if you have questions. And check out my GitHub if you're interested in any of the Python code or the SQL code that helped me to build this.